the board. All right, we are finishing up 10.4, and then we're going to go into 10.5, finish 10.5, and start 10.6 today. So the tests are coming fast and furious now. I think we're at 5 right now, or maybe 6. We're going to do a couple more today, so they're coming fast. So make sure that you've got your note cards going with each of those tests and how you make your conclusions. Okay, so this one is, we look at this. Our text here, our context here is that we're just trying to pick a test. And when we look at this, what we see is a factored denominator. And we had a technique when we had a factored denominator when we had integration. And what was that technique when we had a factored denominator? We did something to bust it apart.
Partial fraction.
Partial fraction decomposition. Right? If we had a factored denominator, that's how we integrated it. If the denominator was not factorable, we used that completing the square technique. But if the denominator was factorable, we used PFD, partial fraction decomposition. So that's what we're going to do here. We're going to rewrite this in PFD, and we're going to see something that hopefully will remind you of a technique that we used a couple days ago. Now, the PFD that you're going to see in the infinite series chapter is going to be really basic PFD, none of the irreducible quadratics, all we can do with the convenient value method. So let's go ahead and PFD this in this summand. So we're going to take our factored product in the denominator. We want to write this as two fractions. So we're going to break this apart into two fractions with constant numerators. And we will end up with a form that should be very familiar. So with PFD, our first step after we set up our structure is to clear the fraction. So we're going to multiply both sides by the denominator that's on the left. And that denominator that's on the left will partially cancel with each of the denominators on the right. So that is our PFD equation. What is the convenient value for this factor right there? Negative 4/3. So we want to know what the k value is that would cause this to be 0. So in your mind, you're plugging in something for k that's going to cause this to be 0. You could think in your mind, set it equal to 0, subtract the 4, divide by 3, and you get negative 4/3. So this is our convenient value, k equals negative 4/3 for that first one. And what about the convenient value for the second one? Negative 1/3, exactly. So those are our two convenient values. So in the top equation here, we're going to have 1 equals, if we plug in this convenient value there, we get 0. So now we're plugging that convenient value in over here, plugging in negative 4/3, the 3's cancel, and we get negative 4 plus 1, which is negative 3. So we have negative 3b. So b will be negative 1/3. Now we plug the negative 1/3 into this equation. The left side will be 1 still. The right side, when we plug in negative 1/3 here, the 3's cancel. We get negative 1 plus 4, which is 3, so we get 3a. And so there are the two constants that we're finding. And that's the extent of PFD in this section. Nothing more complicated than those convenient value technique. I'm just going to use shorthand notation for that summation. We know that it goes to infinity. And we're going to rewrite this as, let's see, a is positive 1/3. So we're going to have 1/3 divided by 3k plus 1 minus 1/3 divided by 3k plus 4. And what kind of series is that? Telescoping. Bless you. Telescoping, we have two terms separated by a minus. And that will be a telescoping series. Now, if you look at that denominator, well, let's focus on, we'll talk about the denominators in a minute. Let's factor out the 1/3. Let's get that out of the way. That'll make our life a little bit easier. So we'll have this setup. So the first part is this term. Second part will be this term. Okay, so this is going to be telescoping. And we know that with telescoping, we can actually find S sub n for a telescoping series. And a geometric series, we can find S sub n. Those are the only two series that we can find a formula for S sub n. So let's go ahead and do that. So S sub n, remember it's the sum of the first n terms. It has nothing, it's not aligned with k. So we still want n terms regardless of where k starts. So the very first term, what's the k value? K value is 4 for the very first term. So I'm going to put the k value and the term number here. So the first term has a k value of 4. So S sub n, first term, plug in a 4 right above here. And I'm going to leave out the 1/3. We're going to leave out the 1/3. We'll come back and include the 1/3 when we find our total sum. But we're just going to focus on the series piece of it. So we're just going to focus on that part for S sub n. So plugging in k equals 4 is going to give us 1 over, plugging in 4, that's 12 plus 1 is 13. Plug in 4 there, and we get 16. Does everyone agree with that? So that's the first term. First term. Second term will have what as its k value? 5. So we started at 4 for k. The next term is the second term. The k value is going to jump to 5. So we're plugging in a 5 here. So we get 16 in this denominator and 19 in that denominator. So we get 1/16, 1/19. Looks like that. Third term, k is 6. So k will be 6 for the third term. That will be, let's see, plugging in 6 here, we're going to get 19. 1 over 19 minus 1 over 22. And then we'll put some stuff in here. Hopefully that's enough. It should be. All right. Let's put the tail end of it down below instead of stretching the page out that way. So let's do 3 more terms. So the dots are coming this way. Let's not put the plus there. We'll put the dots here. So we're going to do 3 more terms at the end just for the heck of it. That should be enough terms. So let's focus on the k values and how the term number relates. So the nth term is going to be here. The term before the nth term is the n minus first term and the n minus second term. So those are the term numbers. And now the hard math, the arithmetic, we have to figure out the corresponding k values. So what is the corresponding k value for the n minus second term? N plus 1. How did you do that?
Subtracted k from the normal number, or the index number, and then added that to the index number.
So the difference between k and the term number is 3. And so if you have the term number, you add 3 to get to the k value, or you can subtract the other direction, doesn't matter. So I have the term number here, so I add 3 to get to the corresponding k value. So adding 3 to this gives n plus 1, adding 3 to this gives n plus 2, adding 3 to this gives n plus 3. So those are the k's that we have to plug in to get those respective terms. So let's do this one. So we're plugging in n plus 1 right up there. Now that n plus 1 is in parentheses. So it's going to be 3n plus 4 in the denominator there. 3n plus 4. And then when we plug in n plus 1 right there, we get 3n plus 7. Because the 3 has to distribute. So 3n plus 7. Is everyone following that? So if you plug in n plus 1 right there, that's 3n plus 3. You have to distribute the 3. 3n plus 3 plus 4. So 3n plus 7. n plus 2, plug in here. That's going to be 3n. So multiply this by 3. 3n plus 6 plus 1. So 3n plus 7. Plug in n plus 2 right here. That's 3n plus 6 plus 4. So 3n plus 10. n plus 3 right there. n plus 3 times 3 is 3n plus 9. Plus 1 is 3n plus 10. So 1 divided by 3n plus 10. n plus 3 there. So multiply that by 3. We get 3n plus 9 plus 4. So 3n plus 13. 3n plus 13. So there is our S sub n. And now we have to figure out the cancellation pattern. And it's pretty easy in this case. As we're moving left to right, second part cancels with first part, second part cancels with first part, second part cancels with first part in the dots. So there's only one preserved part in the front. And similarly, the same number of parts needs to be preserved in the tail. And when we look, it's like, okay, so now when we're going the other direction, when we go the other direction, the first part here cancels with first part of prior, the first part here cancels with second part of prior, first part here cancels with second part of prior, so somewhere there. The only thing that's left is this, the end. So that tells us then that S sub n, so this implies S sub n has a formula, and the formula for it is 3n plus 13. So this is just for the series part, not, we still, bless you, we still have the 1/3 out in front. Okay, so S sub n is that, which tells us S for the series part of it is how much? 1/13. So the limit as n goes to infinity, this part here is going to go to 0. So this will be 1/13. And then our big conclusion, the total sum, because we separated the series from this coefficient of 1/3, so the total sum would be 1/3 multiplied by 1/13, which would be 1/39. So this converges, the series converges. And we know what it converges to. So the only two series that we have that luxury to actually find the sum of the series, the only two series are the geometric and the telescoping. The other series, all we can say is converge or diverge. But this one, we can say it converges to a 39. Okay, so on the exam, I will tell you what test to use. I may throw one on there that I don't tell you, but almost all of them, you can look at the prior exams, I'll tell you. So that's the tricky piece, is trying to decide for yourself. But I don't want you spinning out, so I will give you some hints on that. All right, so let's go to this concept here. We're at this stage of the game, all of our series have had positive terms, And our visualization has been that slope that comes down to the x-axis, so all of the term values are positive. And when we're dealing with series with positive terms, we need to have a gauge on the remainder. And there are a lot of math classes that focus on the remainder of an infinite series. Infinite series are used everywhere. All the computations in calculators and computers are related to computing infinite sums. And so the idea, I mentioned this on Tuesday, I'll just say it one more time. The idea is that when you have a computing device, you don't want to waste computation time. And so what it will do, if you're typing something into your calculator, like square root of e, it's going to look for a series representation, and then it's only going to want to add up the first number of terms necessary. Right? We don't want to spend extra time adding terms that are insignificant. If your display has 10 digits, why compute it to 100 digits? So we want to sort of minimize our computation time by understanding the remainder. And so if we had 10 digits, we'd want the remainder to be small enough to give us accuracy to 10 digits. And in this class, the focus on the remainder is going to be limited to the next section. We're going to talk about alternating series, and we're going to really focus on the remainder there. In this section, we're going to talk about some ideas of the remainder and give you some intuition for it, but we're not going to spend a lot of time on it. When you get into other classes that deal with the remainder, you'll dive into the remainder with these integrals in head first. But for us, the remainder, we're going to talk about it conceptually and then focus on it with one type of series, and that's the alternating series. So the concept is that we've got our infinite series, and we now know really well what S sub n is. Right? S sub n is the sum of the first n terms. But then there's this infinite collection of terms that aren't included in S sub n, right? You have your n minus first, your n plus first term, your a sub n plus 1, your a sub n plus 2, your a sub n plus, all the way out. Right? So the leading terms give you S sub n. We're going to call the rest of it R sub n. So if you have S sub 3, you've added the first 3 terms, and then R sub 3 would be the rest. That would be term 4, 5, 6, etc. added together. And so that remainder, as the number of terms of S sub n increases, right, the number of terms in R sub n decreases. I mean, it's still an infinite number of terms, but so there's a little bit of funny business there. But you know what I mean. If S sub n has 100 terms in it, then the first term for the remainder is going to be that 101st term. So let's take a look. So before you look too heavily at this piece, let's look at some visuals here. Let me see if I can get both of those on the same page. Would be ideal. So we've got our curve. We're thinking about positive values, and the blue rectangles here and the blue rectangles here are representing S sub n. So I have n blue rectangles here. I have n blue rectangles there. The rest, the pink, that's R sub n. So here I'm looking at right endpoints to determine the height of this rectangle. Down here I'm looking at the left endpoint of this interval to create this rectangle there. But there's n rectangles in blue in both cases. Right? You can see that the blue is the same, right? There's the same number. If I count them, there's 6 there. Count them, there's 6 there. So up here, where we use this right endpoint thing, look at these two integrals. So the focus is on the remainder here. So here, a visual representation of the remainder, these pink rectangles, you can see that the remainder is less than the curve integrated from n to infinity. Right? This remainder starts at n and goes to infinity, and you can see that the pinks are an underestimate of that, the rest of this, right? The integral of the black curve. Right? There's some white gaps in there. So the pinks are below the curve. So the pinks are an underestimate of the integral of that tail. So the remainder is less than the integral from n to infinity. Make sense? If you integrate from n to infinity, you get the area under the black curve. Well, the area under the black curve is more than the pink because there's some space there. Now let's look at the next one down here. So if we integrate from n plus 1 to infinity, when we have our S sub n representation ending right here at n plus 1, so we're looking at these left endpoints of these intervals, well, now the pink is an overestimate of the integral of the tail. Right? You can see the pinks going above the black curve. So the pinks are more. The pinks are the remainder, and that remainder is more than the integral of the black curve from n plus 1 to infinity. So the remainder is always trapped between those two integrals. And you'll look at that kind of stuff in a different math class, like a numerical analysis class. But for us, it's just a concept right now, that the remainder can be trapped in between two integrals. All right? And the smaller you want the remainder to be, the closer these integrals get together. Right? The difference between those two integrals, you can imagine them getting tighter and tighter and tighter. And that will minimize your remainder. So that is the concept of the remainder. So we're trying to estimate the value of a series. So why will that not slide? There we go. So that's what this slide is showing, that the remainder is always going to be less than this. So that's the integral we just looked at down there. Here's our infinite series right here. And on the left side, we have our infinite sum plus the underestimate of the remainder. On the right, we have our partial sum, S sub n, and then the overestimate of the remainder. And so that's what this says. This just says that the total sum of the series is trapped in between. If you want to focus strictly on the remainder, then that's the inequality down there. And this is representing the entire sum of the series. You've got your partial sum plus the tail, partial sum plus the tail. One's an overestimate, one's an underestimate. But you can use integration to get a gauge on the remainder. All right, so now we'll put remainder off until we get to the next section. But that's the concept of the remainder. So let's do just a quick little interesting exercise here. Idea is that we're stacking dominoes or bricks. And the question is, can you stack your dominoes or bricks so that the top domino completely overhangs the bottom domino, the lowest domino? And when you look at that picture, it certainly looks like you can. So if you can, then the question is, well, what's the minimum number of dominoes or bricks to do this? If your dominoes and bricks are machined perfectly, you're not all rounded on the edges, can you do this? And the answer is yes. And this is super interesting. So let's focus on the top here. So if we look at that top domino, if you wanted to find the centroid or the center of mass for that top domino so that it could balance totally on this second domino here, wouldn't this, where the second domino is right here, you would want to put the top domino so the dead center of it is right on the edge, right? Right, totally obvious. If we've got that domino, we're going to place this domino. If they're machined perfectly, you would place it so that the center of mass of the top domino is right on the edge of the one right below it. Yeah? Well, then we're going to do the same thing. Now we take these top two dominoes. The orange is the center of mass for the top two dominoes. That's dead center of the top two. That would have to be lined up exactly on the edge of the third domino down in order to have balance. Again, these things have to be machined perfectly. Like you're on a rocket, the Artemis, perfectly machined. Not like a can of soda, not perfectly machined. So then, same thing. We're going to take these top three, and the top three, the center of mass is this red line. That's got to be lined up perfectly with the fourth domino, etc. And so what it will take is 1, 2, 3, 4, 5 to do it. In practice, if you go grab a bunch of dominoes or mahjong things, probably going to take you more than 5, but most people can do it with 6 or with bricks or cinder blocks. But what is fascinating is looking at how much this overhang is. So the obvious question is, well, if I can get one domino completely over the bottom domino, can I get two? Can I get three? And the answer is you can get as many as you want. Because what series represents the overhang? It's the harmonic. And what do we know about the harmonic series?
Diverges.
It diverges. So we can have this overhang amount be as much as you can possibly imagine, because that overhang can go out to infinity. So again, if everything is machined perfectly, you can create a total crazy wave of dominoes, which is not intuitive that that overhang could go to infinity. But that's a good example of the harmonic series, and it's just crazy. But that's true. All right, so that's just interesting. One more interesting thing. One of the most famous functions in math is called the Riemann zeta function. And the Riemann zeta function, if you look on YouTube and you go to like 3 blue, 1 brown, look at some of those really interesting math websites, you'll find all sorts of videos on the Riemann zeta function. One of the primary applications of it is figuring out the density of prime numbers in the positive integers, the density of primes. And when you look at the Riemann zeta function, you're thinking, what does it have to do with prime numbers? So this, so the zeta function in general looks like that. Z can be, in general, a complex number, so an a plus bi. So we have a regular, when we've looked at a lot of these p series, right, 1 over k to the p. So it's like that. It's also like 1 over x to a power, like we did with our improper integration. The crazy thing in our minds is, wait, you can put an a plus bi in that exponent? That's mind-blowing and hard to imagine. So if we focus on when that z value, that exponent, is a real number, it's going to be a p series. So like 1 over k to the whatever, 1.1, 1.5, 10, 12, whatever. Then it's going to be a p series. If you have a positive even integer, you get some of these known series. And you can find the value of these series. It's not easy, but you can find the values of these. So the first one, the sum of the reciprocal squares, infinite series, sum of the reciprocal squares adds up to pi squared over 6. The sum of the reciprocal powers of 4 adds up to pi to the 4th over 90, powers of 1 over k to the 6th, etc. Those are all known if the k power is even. So when you look at these, so these are all examples of the Riemann zeta function. Do you see anything to do with prime numbers there? Right? Nothing to do with prime numbers. We're just adding infinite series. So this infinite series is 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. No prime number connection whatsoever, right? So then here is the most fascinating theorem around. So this over here is called the Euler product. And the Euler product, so this is capital P, looks like a pi. Everything is prime in here. So if you form this infinite product where you only plug in prime numbers, you can actually show that this infinite product equals this infinite sum. Remarkably easy. All of you could do this. If you look up the solution, it's like half a page and it's just algebra. You could do it. This is the connection between a Riemann zeta function, which is just an infinite series that looks like a generalized p series. It's equal to this infinite product. That's the part that's mind-blowing, and the proof is actually shockingly simple. So there's a picture of a Riemann zeta function. It's just a p series. And there's a picture of the infinite product where you're only choosing prime numbers. And so the proof does this kind of sieve thing, which if you look it up, you'll get it. And then if you look at the special case is called the Basel problem, where you add up these reciprocal squares and you get to pi squared over 6. So this video is super fascinating on how, back in the day, that pi squared over 6 was arrived at. You can definitely understand it. It's not hyper complicated, but it's super unintuitive that series should add up to pi squared over 6. All right, and then the connection with the Riemann zeta function and prime numbers is through this, which again, if you look up the proof, you'll be surprised that it's just algebra. It's just algebra 2. It's not even like college algebra. It's just exponents, rules of exponents, really. So super interesting. So if you want to look up some fascinating math, look up the Riemann zeta function. And if you want to get crazy, watch the 3 blue, 1 brown video of the Riemann zeta function. Because there's a lot of money involved in some of this stuff. If you can predict where prime numbers are, there's a lot of money in that with cryptography. Okay, let's go to our next section. 2 more series tests here. We're going to have one called the direct comparison test, and we're going to have one called the limit comparison test. So 2 more series here. 2 more series tests. 2 more tests. We're going to, again, stick with positive terms for now until we get to the alternating series. So we have 2 series. They've got positive terms. We need to understand these 2 concepts. So the series with the A is always the series we're analyzing. So we've got a series, A sub k. That's the one we're given. We're asked, hey, man, does that converge? Does it diverge? So A for analyze. That's the one we're analyzing. And then we're going to create this second series called the comparison series. It's going to be the ones with the B's. So the B's is going to be a series that we create or that we have in our tool chest, like the harmonic. We know that it converges. We know that it diverges, the harmonic. Or it's going to be a P series that we know converges because P is bigger than 1, like 1 over k squared, something like that. So the B series, we know. It's a basic series that we already know converges or diverges. All right? And here are the 2 concepts. If the B sub k series converges and the A sub k series is systematically smaller, the A sub k series must converge. So if we have a convergent B sub k series and the A sub k series is smaller, it's got to converge. Smaller than converging must converge. So if you think in your mind about the B sub k series, if the series converges, you're imagining the terms going to 0 very fast. If the A series is smaller than it, if the terms are smaller than it, then those terms go to 0 even faster. So if we have a series that converges because the terms are going to 0 quickly, and then we take a series that has terms that are smaller, that means they go to 0 even faster, so that A sub k series must converge also. So that principle in our head, smaller than converging converges. That's our summary in our mind. Smaller than converging converges. Now, let's look at the B sub k series and suppose it diverges. So again, the B series is a basic series. We know everything about it. We know it converges. We know it diverges. So the basic series diverges here. That series diverges. If the A sub k series, the series that we're analyzing, is bigger across the board, then it must also diverge. So if the B sub k series diverges, the terms are going to 0, but they're not going to 0 fast, like the harmonic. Harmonic is going to 0, but going to 0 too slow for convergence. And so if the A sub k series goes even slower, it has to diverge also. So B sub k series is going to 0, but it's going to 0 slowly, so it diverges. A sub k's are all bigger. It's got to diverge also. Right? So bigger than diverging diverges, smaller than converging converges. Those are our 2 principles. All right, so this is just some visualizations here. So here is a picture of 1 over k squared. So that's what the blues are representing. So the black dots are the sequence of partial sums. So remember, we have 2 visualizations. The terms are going to 0 for a convergent series. Terms are going to 0 fast, which means the partial sums are going to have a horizontal asymptote. So the terms are going to 0, so when you add them together, you get your partial sums, which are going to create that. You're adding less and less and less and less and less. And so this is a picture of the partial sums for that series. Picture of the terms would be this. It would be down, going to 0. Picture of the partial sums will be that. There's the limit. And so this series right here, it's not a p-series. It's what I would call p-series-ish. It's close, but it's not a p-series. P-series is 1 over k to the p, period. 1 over k, not 1 over k to the p plus a constant. 1 over k to the p is a p-series. But that's really closely related to a p-series, and you would expect it to behave like a p-series. Do you agree that this a sub k is smaller than this b sub k? If you add 5 to the denominator, you've shrunk the fraction. This fraction is smaller than this fraction because this fraction here has a bigger denominator, so it's going to have a smaller fraction value. So this is a sub k. That's b sub k. B sub k is the basic one, the one we know right there. It converges. P is equal to 2, which is bigger than 1. This one is systematically smaller than it, so it has to converge. All the terms are positive. If this converges, well, this is smaller than it. It must also converge. It's going to converge to a smaller number, too. It's not going to converge to the same limit. So less than converging converges. Let's look at the other example. So our basic series up here, that's a p-series. P is equal to a half, which is less than or equal to 1, so it diverges. Or maybe we'll put that in here. So p is equal to 1/2, which is less than or equal to 1, which tells us divergence. This one up here, p is equal to 2, which is bigger than 1, which tells us that we have convergence. All right, so that's the black. The black dots are our basic series. We know that that series is diverging. Those partial sums are going up forever. So now we look at this series. This is our a sub k series. Do we see that a sub k is greater than b sub k? Yes, we do, because taking 5 away shrinks the denominator, which makes the fraction bigger. Right? This fraction is bigger than that fraction because this denominator is smaller. Smaller denominator, bigger fraction. So this is bigger than that. Here is a picture of the partial sums for that one. And our conclusion is bigger than diverging, must diverge. This black set of dots diverges. That sequence of partial sums diverges. This one is bigger than it, so it has to diverge also. So bigger than diverging diverges. Smaller than converging converges. So those are the 2 concepts that we need to master the comparison test. All right, so let's look at an example. P series. P is 3. It's greater than 1. Therefore, it converges. So that's a convergent P series. So this is the a sub k series. So that's a sub k. I'm sorry, b sub k. B sub k is the one we know. It's a basic series. It's a series we know. So that's b sub k. This is the a sub k, the one we're analyzing. We want to know, does that converge or diverge? What we say to ourselves is, well, let's create a series that's similar to it that we understand. And the way that we create this b sub k series is by getting rid of the fluff. If there's some stuff in here that's insignificant, just ditch it. So if we erase this 1, we think to ourselves, oh, well, this 1 is insignificant. Let's get rid of it. So that is going to put us in a case where we have our b sub k is 1 over k cubed. So you build the b sub k series by taking away the insignificant, Defining what insignificant means is kind of hard, but you intuitively know what I mean, right? Adding 1 is pretty insignificant in that denominator. The significant part of this denominator is the k cubed, right? That's going to infinity fast. That's just, a constant. So our b sub k series converges. So what we would like to show then, we suspect that this one also converges. So what we want to show, I'll use a WTS for want to show, we're going to want to show that our a sub k has what relationship to our b sub k? Less than. Because our b sub k series, our basic series, converges. So the one we're analyzing will also converge if it's smaller. So if we can show this is true, then we're done. Then we know the a sub k series converges also. So that's what we want to show. So we're going to put our a sub k in here. We don't know yet. We would like to show that this is true. So we're trying to show this. And intuitively, we already know that it's true because bigger denominator means smaller fraction. But that's not math. We still have to do the math. So now we're going to cross multiply here. So we cross multiply. We get this. And subtract the k cubed. And you should always be able to get down to an inequality that's, you can identify whether it's true or false by inspection. That inequality is true. So this is true. So therefore, the a sub k series converges. Because that is true. So a sub k series always is the one you're analyzing. Okay. Now the obvious question is, well, what if this inequality is false? Does it mean that that series diverges? Not necessarily. It's inconclusive. So if you come down here and you get a false statement, it's inconclusive. Like, just think in your mind, if you made this k cubed minus 1, oh, we don't have to do it in our mind. It's right in front of our faces. So if we imagine our a sub k having a minus there, we choose our b sub k series in the same way. We get rid of the minus 1 because that's insignificant. So we're sort of thinking, OK, ditch that. This, again, you have p equals 3, which is greater than 1, which tells you have convergence. So of course, this series is going to converge. But the problem is we can't show what we want to show. We want to show, this is what we want to show. We want to show that the a's are smaller than the b's, but we can't do it here. Here, that's not going to be true. We're going to come down to false here because this denominator is getting smaller, so this fraction is going to be bigger, intuitively. So when we do our cross multiplication here and subtract, we get that, which is false. So this means that the direct comparison test is inconclusive. And so just like the divergence test, when it's inconclusive, dig deeper. You've got to do something else. And what we will do when we have an inconclusive inequality here, we're going to go to the second type of comparison test called a limit comparison test. So if we can't get the inequality to be like we want it to be, then we're going to go to the second thing called the limit comparison test. We're not there yet, though. So let's look at some diverging things. So if we are looking at this p series-ish right here, same idea. Let's create the b sub k series. Let's create a basic series that we know how to analyze. That basic series, p is 1/3 less than 1, so it's got to diverge. And we got that series by looking down here and saying, hey, this subtraction of -2 is pretty insignificant. So if we ditch that subtraction of -2, we get our basic series up there, which is a divergent p series. So what we would want to show is what? So we take our a sub k, we take our b sub k. What would we want to show? We suspect that this one also diverges, because that -2 is pretty insignificant. So it should behave like this one. So we want to show that the a's are Bigger or smaller than the b's? Bigger. If the b sub k series diverges, our principle is bigger than diverging diverges. So if we can show that this is true, then we're done. If the a's are bigger than the b's and the b's diverge, the a's have to diverge also. So let's try it. So we're going to put in our a sub k expression here. We don't know if this is true or not. We would like it to be true. So we have that. We can do our cross multiplication. Cross multiplication, we get that. We can raise both sides to the third power. We will get that. Subtract the k's. Get down to a numerical inequality that you can solve by inspection. This is true. Therefore, the a sub k series diverges. So bigger than diverging diverges. We have a true statement down here. 0 greater than -2 is true. So this statement is true. So we have that the a's are bigger than the b's. And since the b series diverges, the a series must diverge also. No choice. But then we have this similar thing to what we just talked about a minute ago right here. We're not going to be able to show that the inequality here is the way we want it to be. Certainly, adding 2 or subtracting 2 is not going to really change anything. This one's going to diverge also. But we will not be able to show that it's diverging by the direct comparison test because we're going to get a false inequality here. And if we get a false inequality, again, that's going to be motivation for the limit comparison test. So let's just show that we get a false inequality here. So again, we want to show that a sub k is bigger than our basic series b sub k, which diverges. So the a sub k we put in here. Don't know if it's true or false. K to the 1/3. If we cross multiply, we are going to end up with that. Raise both sides to the third power, and we end up with this. Subtract the k's. 0 greater than 2? False. So again, that means that this test is inconclusive. And if this test is inconclusive, then we go to the thing that we're going to talk about in a minute called the limit comparison test, if that's false. All right, any questions on the basic concepts of comparing two series? Two principles. Smaller than converging converges, greater than diverging diverges. So here is what happens when we have a comparison that is inconclusive. So the inequality is not what we want it to be. We've got to do a little more digging. We're going to do this. So we've got our two series. The B sub k series, our basic series that we understand. The A sub k series is the one we don't know. We're trying to prove whether it converges or diverges. DCT, direct comparison, is inconclusive. So we're going to form a limit of the ratio. So we're going to take the ratio, the A sub k series, the unknown, with the known. Take that ratio, take the limit as k goes to infinity. And if you get a positive real, that's what that means right there, positive real. Get a positive real. Then both series do the same thing. They both converge or they both diverge. This should remind you of the integral test. The integral test said if the improper integral converges, then both the, what did it say now? If the integral converges, if it's a positive real, then both things do the same thing. They both converge or they both diverge. So if the integral converged, the series converged. If the integral diverged, the series diverged. So the integral test said that the series and the integral do the same thing. That's what it said. If the series and the integral do the same thing, if the series and the integral, they're either going to both converge or both diverge. The integral and the series do the same thing. Both converge, both diverge. So it's similar to that. If we get a limit here, so a positive real number, then both converge or both diverge. So they do the same thing if we get a positive real. So the thing we have to remember is that this positive real doesn't mean that the a sub k series converges. It means that it does the same thing as the b sub k series. Okay, if it's positive real. Now, if the limit is 0, and that's going to be the part of this test that we use the most, that first part. That's the most important part of it. The second part, if this limit is 0, so we're imagining series where both the b sub k's and the a sub k's, they're going to 0. All right? We're not imagining outlier cases where if the terms aren't going to 0, then we already know they diverge because of the divergence test. So we're imagining series that are in that purgatory land where, okay, the terms go to 0. Do they go to 0 fast enough? So we're in that state right here. So if this limit is 0, we're imagining both the a's and the b's are going to 0. Just trying to determine if they're going to 0 fast enough. So they both are going to 0. If this limit is 0, doesn't that mean that the a's are going to 0 faster than the b's? If this limit is 0? So if they're both going to 0, the a's are going to 0, the b's are going to 0. But if this limit value is 0, that means that this numerator must be going to 0 faster than the denominator. Right? If that limit's going to be 0, and both of these are going to 0, and we get a limit of 0, the top has to be going to 0 faster than the bottom. If the bottom's going to 0 faster than the top, the limit's going to go to infinity. So if the limit is 0 and the b sub k's converge, well, I just said that the a's are going to 0 even faster than the b's if this limit is 0, then the a's must also converge. Okay, so most important cases up here, this is kind of an edge case. If the limit's 0 and the b's converge, the a's have to converge. This case, another edge case, if this limit is infinity and the b's diverge, then the a's have to diverge. So same idea. The a's and the b's are both going to 0. Question is the speed. So if this limit is infinity, it means that the a's are going to 0 slower than the b's. If the b's diverge, then the a's have to diverge also. So these two edge cases are going to take you a lot more thinking to understand. The primary case we're going to focus on is this top one. Okay, so we have a p-series-ish looking thing. We know that the direct comparison test gave us inconclusive. The b sub k series is 1 over k cubed. So this is b sub k. P is 3, which is greater than 1, which tells you convergence. And you can see, hopefully now, why the direct comparison test is not going to work. Because this series has smaller denominators, so it has bigger fractions. This series converges. This a sub k is not going to be less than the b sub k's. So the inequality is not going to work. So let's try the limit comparison test. So the limit comparison test says take the limit as k goes to infinity of a sub k divided by b sub k. So that is the limit as k goes to infinity. A sub k is one we're analyzing. And if we're going to divide by b sub k, there's b sub k, we're going to multiply by the reciprocal. And what is this limit going to be? Three different ways. L'Hopital, Powers, whatever, divide by highest power k. Limit is 1. So, the limit is 1. This is a positive real. So it's an element of the positive reals. So that notation again, the epsilon stands for element. And R plus means positive real numbers. The 2-barred R means all the real numbers. R plus means the positive reals. That's the same thing as saying L is between 0 and infinity. It's a positive real. That's what that means. So it's a positive real. So this tells us that both series do the same thing. If you get a positive real with the limit of that ratio, it means that they're behaving in tandem. They're connected. If you get a positive real, they're going to do the same thing. So our conclusion is that therefore the A sub k series is going to converge. So A sub k series is always the one that we're analyzing. You could be a little bit more generic and say both series converge. Either of those is totally fine to say. So this general notation just means the series that you're analyzing. The A sub k series is always the one you're analyzing. All right. So similarly with this one, we know that our B sub k series is the harmonic. So this is B sub k in here. This is a P series where P is 1. This is less than or equal to 1, which tells us that we have divergence. So if P is bigger than 1, you have convergence. So remember that we want to distinguish. We want to be able to identify what is it about P that's important. Well, if it's bigger than 1, you have convergence. If it's less than or equal to 1, you have divergence. When P is equal to 1, you have the harmonic. You could also say P equals 1, which is harmonic. So another line of reasoning, which is totally fine. You still need to identify P, but then you could say that it's harmonic, which tells you divergence. You could do either the black or the blue. Doesn't matter. P is 1 if that special case of the harmonic, which we know diverges from the integral test. Totally fine. Either of those. Identify P, compare it to 1, or identify it and say, hey, that's the harmonic. Either way. So diverges. Now, so you would want to show that the A's are bigger than the B's since the B's diverge, but you can't. This is going to be false. We went through the math already. It'd be false. Bigger denominator means smaller fraction. So here the A's are smaller than the B's, not bigger than the B's. So we can't show that. That's false. So then we go to the limit comparison test. So the limit comparison test says take the limit as k goes to infinity of A sub k over B sub k. So we'll get the limit of A sub k is the one we're analyzing, so 1 over k plus 1. Dividing by B sub k means multiplying by its reciprocal. So we get the limit of k over k plus 1, which is 1. Okay. Now we have to make a conclusion for the limit comparison test. We get a 1. Limit comparison test says that if you get a number that is a positive real, so just like we did up here, positive real, both series do the same thing. So this tells us that the A sub k series diverges. Or you could say both series diverge. You could say either one of these two things. So the B sub k series diverges. This is a positive real. So the A sub k series must diverge also. They do the same thing. All right, let's go ahead and take our break. Take a 10-minute break. And then we'll reconvene. Go ahead and try to attack that top problem. So the a sub k is the inside of that series. That's what we're analyzing. So I want you to try to figure out b sub k. So to choose b sub k, you remove insignificant terms and simplify. There's only one insignificant term now, that's plus 2. So then simplify, and that's going to be your b sub k. And then try to use the comparison test and see if the inequality is favorable. And if it's not favorable, then go to the limit comparison test. Oh, this is so exciting. I'm dying to see what you do. I'm dying to check out your b sub k's. Ooh, you can't let it. So that, yep, now simplify.
If you subtract it, you're in the negative exponent.
Shove it in the denominator so it's in the form of a p series. Okay, see it? See it? See it?
That's so neat. You get to a negative 3 over 7.
Yeah, get rid of the 2 and then simplify. And so when you simplify it, you need to simplify it in a way that is basic, a way that you can analyze it, i.e. p series. Yeah, so now shove that into the yeah, good, good. Now combine your exponents and then help anyone who's brain.
I can't help. Excuse me. They're on their own.
Oh, wow.
I need help.
Brutal. Brutal. She's not trained.
I'm not trained. Yeah.
Come on. So you started out right. Take what it says.
Well, I just wrote down some questions.
Oh, you didn't do anything? Oh, I think I saw that. I thought the 2 was going on. Take away the 2. Take away the 2 and simplify. And the way that you simplify, you need to put it in a form that is friendly. i.e. p series.
Oh, 3 over 2 is greater than 1. Yeah, so
Yeah. That feels wrong there. So this is right. That's right. But when you take half away from 2, you get 3 halves. Right. There we go.
So should I choose this?
So is your p? So is your b series converging or not? Yeah, that's right.
And then should I simplify this?
Nope. No, you can't simplify that. Nope. So you're just going to now try to show your inequality that the a's are either less than the b's or greater than the b's, depending on what your a's do. So write it as p series. So p series is 1 over k to the t, not k to a negative number, even though you could write it that way. So, oh, you went to limit. Okay, let's see. I don't know. I can't remember the answer. So the b sub k that we're going to choose, b sub k, we get rid of the deuce. Bye-bye, 2. And then we move everything into the denominator so that we have it in the form of a p series. So that 1/2 as the exponent of k in the numerator, when it moves down as a negative 1/2. So we're going to have 2 minus 1/2, which is 3 halves. So that's going to be your b sub k. And this is going to correspond to a p-value of 3 halves, which is bigger than 1, which means bigger than 1 is converging. So for a p series, greater than 1 converges, less than or equal to 1 diverges. So this converges. So our hunch is that the a sub k series also converges. So would we want to show that the a's are bigger than the b's or less than the b's? less, the B's converge. So the B series converges. We can show the A series converges if we can prove that the A's are always less than the B's. So that's what we would want to show. Can we show it? I don't know. Let's plug it in and see if it's true or false. So we don't know. We'll put a question mark there. And this is going to be 1 over k to the 3 halves. So we've got that. Cross multiply. So we'll get k squared less than or equal to k squared plus 2. So 0 less than 2. True or false?
True.
True. Done. So this is true. And because that's true, that means the series that we're analyzing, the A sub k series, does the same thing as the B sub k series, so that converges. So you could write it like that. Or you could write it this way. You could say both series converge. Either one of those conclusions. Now you could also go to the limit comparison test and show it with limit comparison also. So there's a lot of series for which the direct comparison doesn't work, but the limit does work. There's a lot of series that both will work. And there's some series where the direct comparison works, but the limit doesn't. So you want to be able to do both, because there are some unique cases that only one will work. OK, somebody tell me what you think B sub k is going to equal in this case. I think I heard it. All right, 1 over 3 to the k. Is that a P series? No. All right. P is 1 over k to the P. Here the k is in the exponent position. What kind of series is this? Geometric. Geometric. We would write it in this form, typically, 1/3 to the k. So the series would look like this. This would be our B sub k series. Our B sub k series looks like that. And what is that series? Geometric. And what is the piece of it we have to identify?
R.
R. And what would R be? 1/3. So this is a geometric series. And so I know you know this is a geometric series if you put in R. You could also indicate it somehow if you wanted. But if you use the letter R there, I know that you're thinking of it as a geometric series. So now we have to do similar to what we did with the P series. Once we identify P, we need to compare it to something to make a conclusion. What do we compare this R to? And what's our conclusion? It's less than 1, so our conclusion is? Converges. Good. So this is tricky because P series bigger than 1 converges. G series less than 1 converges. All right, so we've got that dyslexia thing going. We've got to be a little careful. So in your mind, with a P series, remember that you're analyzing the denominator. Whereas in the geometric series, you're really analyzing the numerator. Right? You're analyzing 1/3 to the k. You're up top. You're not down in the denominator. So in the denominator, for a P series, bigger than 1 converges. But for a geometric series, the common ratio, that's more in the numerator. Or you can think of it as 1/3 to the k is up top, and below there's a 1. It's up in the top. That k is up in the top. So geometric series, less than 1 converges. P series, greater than 1 converges. So we have to keep those two straight. Okay. Okay. So what do we suspect is true about the A sub k series?
It's going to be less than B sub k.
So if we can show that it's less than B sub k, it's also going to converge. So that's what we would want to show. Let's see if we are fortunate. So we want to show that the A sub k's are smaller than the B sub k's. We know that the B sub k's lead to a convergent series. So the a sub k. Will we be, intuitively, when you look at it, are we going to be able to show that this is true?
Yep.
This denominator with the plus 2, that denominator is bigger. If the denominator is bigger, the fraction is smaller. So yeah, we're going to be able to show it's true. So once again, generally the math is confirming our intuition. Or at least we want it to get to that point. And so then we have 0 less than 2. This is true. That means we're done. This means the a sub k series converges. You can say that. Or you could say both series converge. Either one of those. Now, one subtlety that we have to be a little bit careful of is there's a difference between saying the b sub k's converge and the b sub k series converges. Right? Because there's two things. There's the sequence of terms, like the b sub k's are a sequence of terms, and those may converge to 0. Just because the b sub k's converge to 0 doesn't mean the b sub k series converges. Like with the harmonic terms converge to 0, but the harmonic series diverges. So we have to be a little bit careful with our terminology when we talk about, if we're being loose and talking about the b sub k's. We need to make sure, are we talking about the b sub k sequence or the b sub k series? So the b sub k sequence converging to 0 is an inconclusive divergence test. The b sub k series could diverge or converge with a convergent b sub k sequence. So we just have to be a little bit careful here with the terminology. Know whether we're talking about a sequence or a series. All right, so this one, a little bit harder because the insignificant term is not a constant. It's pretty obvious when the insignificant term is a constant. So here, when we look at the denominator, we have two functions that are both exponential in nature. One of them dominates, though. Which one goes to infinity faster?
3 to the k.
Yeah, 3 to the k is going to dominate 2 to the k. 3 to the k is going to go to infinity faster than the 2 to the k. So my hope is that choosing this, so once again, this is geometric just like the last one we looked at. This is what I'm hoping will work. So that's going to be b sub k. So the series b sub k is a geometric series with r equal to 1/3, which is less than 1, so we have convergence. Okay, so that we're familiar with. Everyone okay with that? So geometric series converges. So what we want to show, once again, if the b sub k series converges, we're hoping that the a sub k series converge, and we're hoping that we can show this inequality. This would make our lives the simplest. That would make our lives the simplest. Will it give us what we want? So we cross multiply. Okay, the 3 to the k's cancel. We have, if I add the 2 to the k's to the left, just have no negative numbers in there, we would have that. And that's false. 2 to the k is not under 0. It's not less than 0. All right, so this is false. Sad face. That means dig deeper. But I don't want to dig deeper. So we go to the limit comparison test. And we form the limit as k goes to infinity of a sub k over b sub k. when the direct comparison doesn't work for us, that's what we're going to do. I'm just going to move that over a little bit. And when we form this limit, we have the limit of a sub k, so that's when we're analyzing, it's the original. So 1 over 3 to the k minus 2 to the k. Dividing by b sub k means multiplying by the reciprocal. I'm going to use this form of the b sub k. You could use this, but then that's a little complicated. We want to sort of distribute that k to make our limit analysis a little easier. So we'll do that. Okay. So we have 3 to the k over 3 to the k minus 2. We want to analyze that limit. So one thing that we did with polynomial fractions, with rational functions, was divide by the highest power of x. And if you generalize that concept, the idea is that you divide by the dominant term. So if we do that here, if we divide by the dominant term here, if we divide everything by 3 to the k, we'll have that. So if we divide by the dominant term, 3 to the k dominates, it goes to infinity fastest, divide everything by it, notice that we can simplify, or at least rewrite, this piece down here to be 2/3 to the k. And we're taking a limit as k goes to infinity. And what's true with 2/3 to the k as k is going to infinity? That's going to go to 0, because that 2/3 is less than 1. You take a number less than 1 and you do repeated multiplication, it gets tinier, goes to 0. So this little piece right here is going to 0, which means our overall limit is 1. I feel like every time we've done the limit comparison test, we've had a limit value of 1. I need to change my example so that we don't, so it's not always 1. Okay, now conclusion for limit comparison test. Limit comparison test says if you get a positive real number, that's what we got, positive real number. This is a positive real number. What's our conclusion?
Sum of a sub k also converges.
Also converges. So the sum, the one we're analyzing, the sum of a sub k, does the same thing as the sum of the b sub k's. The b sub k series converges, so the a sub k series converges as well. So therefore, the a sub k series converges. Or you could say both series converge, whatever. So the key, though, when you're analyzing the conclusion for the limit comparison test, just make sure that you do this positive real. What, this thing is finicky. That positive real thing. Don't like it. Don't like it. Leave it there. That's fine. So positive real, both series do the same thing. Okay, let's try this one. When you look at this one, you have that same sort of scenario. You've got two functions here. One of the function dominates, which means it goes to infinity faster than the other. And which one of those functions goes to infinity faster, 4k or root k?
4k.
4k, that's linear. Linear is going to go faster than a quadratic. A quadratic, or excuse me, not a quadratic, a square root is going to go to infinity slower. So our thinking, when we come up with our b sub k series, is that we are going to ditch the square root, and we're going to be left with this. So that's our b sub k. Now, you have choices on your b sub k. You could also say, hey, multiplication by 4 is also kind of insignificant. So you could actually choose your b sub k to be just 1 over k, possibly. Now, one thing that I've noticed by doing a lot of these problems is that sometimes leaving the multiplier in is helpful for the inequality. What we've seen is the inequalities work in our favor when things subtract off. And if the original has this 4k in there, but then for our b sub k we take away the 4, we're not going to have 4 k's that might line up. You might have a 4k on one side and a k on the other. So multiplicative insignificance often is better to just leave in so it'll help with the inequality. So let's just leave it in for now, and if it doesn't work, we can change it. Now you certainly can factor out that 1/4 here if you're trying to analyze the b sub k series, right? Because that 1/4 multiplication doesn't change convergence or divergence. So what kind of series is this?
Harmonic.
It's harmonic. And what's the value of p? 1. So you could say that this is harmonic. And that means that it diverges. Do that. Or you could say p is less than or equal to 1, therefore it diverges. Either way. So our hunch is that this thing probably diverges also. Let's see. Let's try our inequality thing. So we would want to show that the a's are smaller or bigger than the b's. So greater than the b's, because bigger than diverging diverges. So if the b series diverges, if we could show that, then we'd be golden. So let's see if we can show that. So a sub k is this one. We don't know, so I'll put a question mark. B sub k is that one. So when we do our cross multiplication, we get 4k greater than or equal to 4k minus root k. And those 4k's are going to cancel. So you can see right there, if you made this just 1 over k and left out the 4, these things wouldn't cancel. Because you'd have a 4k on one side and just a k on the other. And you want things to cancel. So the question then is 0. We have that. And if we want to get rid of the negative exponent before we do our analysis, we could add the root k to the other side. Oh, is that true or false?
True.
True. Wow. Okay, that's nice. So when it's true, we can make a conclusion right away. So if that's true, what's true about the a sub k series? So it's going to do the same thing as the b sub k series. The b sub k series was harmonic, so it diverged. So we get that both of these diverge. Yeah. All right, you all try this one. So this time we have two functions, but they're multiplied instead of added, but you can still sort of see that there's two functions, and one of them is going to dominate the other. So get rid of the one that doesn't dominate. Get rid of the beta. The big question is, will the inequality hold? You can divide by positive numbers and not, not screw up the inequality. If you're dividing by positives, you don't have to reverse the inequality. Yep. L and K. Well, doesn't it depend on what's natural order 2? What's natural order 3?
Wait,
Right?
oh, it's 0.
Well, let's see. So if
Wait,
we
no. Natural log of 1 is 0.
natural log of 1 is 0, but natural. So let's just take a glance.
Oh, it's E.
So, oh right.
Ln of B is.
1.
Ln of E is 1.
So,
Okay, so the one thing to remember is that if we have a series and you chop off the first finite number of terms, that's not going to change convergence or divergence, right? So if we have this series that starts at 2, if you started at 2 or 10, that's not going to change convergence or divergence. So the inequality we would like to show here, we would like to show that the a sub k is smaller than the b sub k. That's what we would like to show. And there becomes a slight question here. Do we mean that it has to be less than the b sub k always, or eventually? And the answer is eventually. Like if it's not, if the inequality doesn't hold for like 2 or 3 or 4 or 5 values of k, that's okay. That's all right. If it holds eventually for the tail, that's actually the important thing for an inequality with an infinite series. Because you can always chop off the leading terms, and that doesn't affect convergence or divergence. Those are insignificant. So let's see what we get here. So we see that the k squareds are going to cancel, and we get this inequality that looks like this. And if you plug in 2, natural log of 2 is less than 1. Natural log of e is equal to 1, and then natural log of 3 is greater than 1. So this is true if k is greater than or equal to 3. Then it's going to be true. So it's eventually true. So it's going to be true for all except the very first value of k. So this is okay. This is all right. You don't have to go to the limit comparison test here. So it is eventually true. So we can then make the conclusion that therefore the a sub k series is going to do the same thing as the b sub k series and converge. You could also go to the limit comparison test, but you don't need to here if that inequality is eventually true. All right, so that is how this comparison thing works. Let's take a look at a series that's in expanded form here. Any of this analysis that we've done requires our series to be in summation notation. So if they give us one that's expanded like this, unless they're being really cruel, it should be pretty simple to convert it over into a summation notation. So let's see, can we convert this to summation notation easily? And what we notice here is that the numerator and the denominator are linked. And the denominator is always the power. So we could write this as k over k plus 1 to the k plus 1. We could do that. The denominator is always up there. So that would work. We don't love having a k plus 1 up there. It'd be nicer if it was just a k. But we could do that. And here k would start at 1. So that's one way to do it for sure. We could also try to be clever with subtraction, or we could say, well, let's make this k as the denominator and the exponent, and then what would we put for the numerator there? K minus 1. So we could do this instead. We could say, okay, let's do k minus 1 and k there. And then what would k start at? K would start at 2. Either of these is correct, and we'll be able to answer either of them in either form. So this one will be easier, though, because the power is just k. What is the very first thing we should at least consider when we're looking at an infinite series? The divergence test. So the divergence test, we should be thinking, do the a sub k's go to 0? If the a sub k's don't go to 0, we know it diverges. And we've seen a lot of things in this form over the semester. What is the limit of this as k goes to infinity? No. That's the pip, the little trap door, right? What form does this have? It has the form of 1 to the infinity, right? So 0 to the infinity, not indeterminate. 2 to the infinity, not indeterminate. 1 to the infinity, indeterminate. So this is indeterminate, but if you distribute the k right there, I'm gonna rewrite it strategically like this. What is that limit?
Negative e.
Close. E to the negative 1. That negative 1 is going to be the exponent. So it's going to be e to the negative 1, which is 1 over e. Right, so remember that we take that number there after a plus. That's got to be a plus. And then we take that coefficient right there. So it's negative 1 times 1. This is not equal to 0. Therefore, diverge. So this is diverging by the divergence test. All right. All right, this thing, this one's a little bit funky. We can use a comparison test here. And the question is, what is your b sub k going to be? And I want you to think back to like the improper integral idea. If we had 1 over natural log of k, certainly these terms are going to 0. Right? Denominator is going to infinity, but they're going to go to 0 slower than 1 over k. Because natural log of k goes to infinity very slowly. It's going to go to infinity slower than just k. So I want to just see if we can compare this. So here we have p is equal to 1, which is the harmonic, which is going to diverge. So we already know that that one diverges. And if this one is going to, if the fractions are going to go to 0 even slower, we know it's going to diverge. But let's see if we can actually make the comparison test work here for it. We could do it with other tests if necessary, but let's see if we can do the comparison. So we would want to show that the a sub k's are bigger or smaller than the b sub k's. Bigger, because the b sub k series diverges. So we want to show that the a sub k's are bigger than the b sub k's. And yeah, it's easy to sort of start getting a little bit tangled up, but that is the basic principle. All right, the basic principle is that if the b sub k series diverges, we want to show that the a sub k's are bigger. And we have this. Now, we're not going to be able to rewrite this so that we have a numerical by inspection type of situation like we've had in most of them. So here we have to think a little bit back to calculus. Think a little bit, maybe think graphing. So a picture of y equals x or y equals k is that. The natural log function goes through here. And it looks like this. So that is going to be true. That is going to be true. And in calculus, sometimes you prove this with a method that's a little bit, there's a technique called proof by induction. And the idea, sometimes you use that idea, proof by induction. Like if you look at x equals 1, you can show that that's true, right? If you look at x equals 1, we know the natural log of 1 is 0. Natural log of 1 is going to be less than 1. And then what's true about the difference between k and natural log of k? You can see that the difference is getting bigger. So if you show that this is that the k let's call it x. Y equals x is bigger than y equals natural log of x right here. And then you form the difference, x minus natural log of x, and take the derivative. You can show the derivative is always increasing, which shows that they're getting wider and wider apart. So you can use a Calc 1 technique to prove it. For us, it's fine to just look at this graph, and we can say that this is true. We don't need to go back to Calc 1 and prove it. So that is true, which tells us that the original series also diverges. So we have that. So we can use comparison test for some situations where we're not even taking away anything that's insignificant. 99% of the time when you build your B sub k, you're taking away stuff that's insignificant. Here we're just using a little bit of logic. It's slightly different. All right, so we've got these last couple of examples. What do you think the B sub k should be here? So the 5 goes away, and then we have k to the 2 over k to the 6. Then we simplify. And when we simplify k to the 2 over k to the 6, we want to sort of push everything into the denominator so it's in the form of a p series. So 1 over k to the 4. So this is a p series. P is 4 greater than 1, so converges. All right. Are we going to be able to use the direct comparison? So if you think about your B sub k, you could, before simplifying your B sub k, if you think about it like this, you should be able to decide whether the direct comparison is going to work or not. Will the direct comparison work? Will these A's be smaller than these B's? Well, this has a bigger denominator because you added 5 to the k to the 6. Bigger denominator means smaller fraction, so we will be able to show that it's going to be true. So we want to show, and we will be able to show, that the A's are less than the B's. So let's do the math. And it might be easier to use that form of the B instead of the simplified form. Like, it's totally fine to do that. It's going to work either way. It does not matter. But when you do it this way, right away, we can say, oh, the k to the 2's, those cancel. And so we will have this. Something's fishy there. That should be a k to the 6. So then we get 0 less than 5, which is true. So that tells us that we have an A sub k series that does converge. What do you think about that one right there? Do you think it's going to converge or diverge?
Converge.
So that's going to converge. So we know that 1 over k squared converges. That is that Basel problem. It converges, now we know, to pi squared over 6, 1 over k squared. So the concept here is that the numerator is not a constant, but it's a bounded function. And a bounded function acts like a constant when you have things going to infinity. So this will converge. The choice that we're going to use for b sub k will be the 1 over k squared. Let's see if this is going to work. So p is 2, which is bigger than 1, so you have convergence. So let's see. Are we going to be able to show the inequality is true? We would want to show that the A's are smaller than the B's. Is that going to be true? So the k squareds in the denominator cancel. Is inverse tangent of k less than 1? Eventually. What do you think?
No.
So if we think about the graph, well, let's just focus on the right-hand side of the graph. The right-hand side of the graph for arctangent looks like this. What is that asymptote at? pi over 2. And is pi over 2 bigger or smaller than 1?
Bigger.
Bigger. So these values, arctan, the values are going to be eventually bigger than 1, but below pi over 2, but bigger than 1. So that inequality is false. This is false. So we are going to go to the limit comparison test. Let's see what happens when we go to limit comparison test. So limit comparison test, we're going to take the limit of a sub k divided by b sub k. So that's going to be the limit of arctan of k divided by k squared times k squared over 1. And what is that limit? So the k squareds cancel once again. Oh, limit of arctan, we know, we've done it a million times. That thing goes to pi over 2. So we finally have a limit comparison test where we don't get a limit value of 1. But what is our conclusion? So pi over 2.
So it's real, so it does the same thing.
So it's a positive real, which means that both do the same thing. So positive real, so that means both series converge. So you could write it like that, or you could say the series a sub k converges. But we have to put that little caveat in there. It's a positive real. Somehow you have to indicate that it's a positive real, which means convergence. So those are the comparison tests. We have another type of special series that we are going to take a look at next. All the series up to this moment have been positive valued. All the terms are positive. We're about to change that. The first series that we're going to look at that doesn't have all positive terms is going to be called the alternating harmonic. So the alternating harmonic, half the terms are positive, half are negative. The terms are alternating. All right. So the question is, does that alter, if you throw in these minuses, does it change the convergence? So we know that the harmonic series diverges. Here's the alternating. Putting in those minuses, does that offset some of the plussing to give you a finite answer, to give you a limit? Well, here's a picture. So the red squares are the terms. So the first red square is up here at 1, and then minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth. So the terms of the series are going to 0, which they have to if it's going to have any chance of convergence. The terms have to go to 0. So it is going to 0, so the divergence test is inconclusive. It might converge. Well, here's a picture of the partial sums. So there's 1. The first value is just the first term in the series. And then 1 minus a half brings us down here to 1/2. And then we add a third, subtract a fourth, add a fifth, subtract a sixth, add a seventh, subtract an eighth, etc. And you can see from the picture that, ooh, that alternating harmonic converges. And that alternating harmonic, if you looked at a table, you would see that it's going to converge to natural log of 2. So the harmonic diverges, but the alternating harmonic is going to converge to natural log of 2. Okay. So here is a picture of the partial sum, or at least here are the partial sums: 1/2, 5 over 6, 7 over 12. We are not going to be able to come up with a pattern for this S sub n. We can't. You can try. And there is a pattern for the alternating harmonic. It's very hard to get to, though. So you could show that this sequence of partial sums does converge to natural log of 2. It's hard, but you could do it. We're not going to do it in this class. We're just going to say that. So the alternating harmonic, we've seen a picture of the partial sums. We can see that they converge. And we'll take it on face value that it converges to natural log of 2. We're not going to prove it. That leads us to a very simple test called the alternating series test. And you will be shocked at how simple this test is. If we have an alternating series, we have two pieces to it. We have the alternating part, and we have the a sub k part. So the first piece that we have to get really clear in our mind is that the a sub k does not include the minuses. The a sub k is the positive part of each term. It's the magnitude of each term. So we're distinguishing between the sign and the magnitude of the term. So when we look at this, a sub 1 is 1, a sub 2 is 1/2. The minus is not included in the sequence of a's. All right, so we're going to just distinguish between the two. So for an alternating series, the switch is not part of a sub k. Now let's take a look at this theorem. Let's look at this test. So the first test is just the divergence test. The first step, just the divergence test. We're going to take the limit of a sub k, so ignore the minuses. If that's 0, i.e. inconclusive divergence test, then we go to step 2. If that limit's not 0, diverge instantly. And the next step, all we need to show is that the terms are getting smaller. If you look in some old books, the alternating series test is one statement. It says the limit of a sub k, or they'll say the a sub k sequence is decreasing to 0. Decreasing to 0. Then it converges. If the a sub k sequence is decreasing to 0, then it converges. That alternating sign is very powerful. So if the a sub k's go to 0 and the terms are getting smaller, then it converges. That's it. So the theorem, when applied to this, the alternating harmonic, the a sub k is the 1 over k. It's not the switch. So a sub k is everything but the switch, so it's just 1 over k. That limit's 0. And now all we have to show is that the terms, ignoring the switch, are decreasing. They're decreasing to 0. So we want to show that the terms are getting smaller. So we put in our a sub k plus 1. We just add 1 to the k. Cross multiply. That's true. Therefore, the alternating series, the alternating harmonic, converges via the alternating series test. So that's it for the alternating series test. We first do the divergence test, and then we show that it's decreasing. So let's try this one. So first step, the limit of a sub k, as k goes to infinity, a sub k, I'm going to say it like 5 million times because it's so tempting to want to put the minus sign in there. But we don't. So it's everything but the switch. That's a sub k. And what's the limit of that? 0. Now, if this switch was not here, we would have a p series, 1 over k to the half. And if we had no switch, so we had 1 over k to the half, would that series converge or diverge?
Diverge.
P is equal to 1/2, which is less than 1, so it would diverge. Right? P series only converge if p is bigger than 1. So let's see, does the switch change everything? And the answer will be yes. So now we want to show that the terms are getting smaller. Now it's true that you could use a greater than or equal to here. All the series we're looking at, though, to get the, like I've mentioned before, to try to get a series that has terms that are flat and then going down, it's virtually impossible for the functions we deal with. So a sub k is 1 over root k. We want to show, if possible, that that's bigger than the next term. Cross multiply. Square both sides. Subtract k. Almost all of our inequalities we can get down to a numerical inequality that we can claim is true or false by inspection. This is true. 1 is greater than 0. So our conclusion is that the series that we're analyzing, so this is a little tricky here because it's nice and simple to write the series A sub k converges, but with an alternating series, the A sub k doesn't include the switch. So if you were going to write it in this form, you would want to do this, converges. You could just as easily instead just say converges. Instead of identifying the series, you could say either one of these things. This would be sufficient though, just converges. You just have to remember the switch is different than A sub k. But that is the alternating series test. So that alternating sign changes everything. Right, we have now you can imagine every single P series that diverges. Well, if you put a switch on it, then it's going to converge. Right, because the terms are all going to 0 already. It's just that they weren't going to 0 fast enough. The alternating series test simply says if the magnitude of the terms is going to 0, then converges. So the alternating series test will turn a bunch of divergent P series into convergent alternating series. So that putting in the minus can't be underestimated. All right, this series looks like it's not an alternating series at first. But then if you think more carefully, when you plug in odd values of k, cosine of an odd, let me say that again. Cosine of an odd multiple of pi is going to be -1. Cosine of pi, you're over on the left side of the unit circle. Cosine of 3 pi, 5 pi, 7 pi. Then you're on the right side of the circle at 0, 2 pi, 4 pi, 6 pi. So that really is just a switch. So the first part of the alternating series test, the divergence theorem part of it, divergence test part of it, that is A sub k. A sub k is just the 1 over k squared part. And that limit is 0. So that's the first part of the test. That checks. Okay. Now we go to the second part of the test. If that was not 0, we would conclude divergence and we'd be on our merry way. If that's 0, that's basically inconclusive. We have to do more work. So now we want to show that the terms are decreasing. So we want to show that A sub k plus 1 is smaller than A sub k. And remember, we're not dealing with the switch with these. So we're not dealing with the switch. A sub k is just 1 over k squared. 1 over k plus 1 squared is going to be A sub k plus 1. And we don't know if it's true yet. So we'll put a question mark. So the A sub k's don't include the switch. Cross multiply. We're going to get a true statement. We can take the square root of both sides. With an inequality, if everything's positive, you can take the square root of both sides. And you don't upset the apple cart. Right? If everything's positive, you can take the square root of both sides. So k plus 1, k, subtract the k. That's true. We're done. So therefore, converge. So 2 steps. First step is very familiar to us, the divergence test. And then we want to show that the sequence of terms is shrinking in magnitude. All right, things are starting to look ugly. Got that. Let's see if it is as ugly as it appears. So the limit of A sub k, as k goes to infinity, well, that's 0. That checks pretty quickly. All right, the switch is the numerator. Numerator is just 1 for A sub k. And that denominator, natural log of k, quantity squared times k, that's going to infinity, so the fractions are going to 0. Second part looks to me like it's going to be harder. So we want to show that the sequence of magnitudes is decreasing. A sub k is 1 over k natural log squared of k. Now if we plug in a k plus 1, this is going to get a little ugly. K plus 1 for each of the k's. So we have that. Let's come up here. Let's cross multiply and then we'll start, well, let's start thinking now. So when we look at this, we have this coefficient expression, k and k plus 1. And then we've got these hideous natural logs in here. And there's no way to cancel those logs. There's no canceling between a log of k and a log of k plus 1. There's no canceling. What we could do, if we stack them, we could pull out the power. And so let's do this. Let's put the k's on one side and the natural logs on the other. So let's write it like this. Let's write this as k plus 1 over k greater than, we'll go natural log squared of k over natural log squared of k plus 1. So on the right-hand side, let's fiddle with that for a second. So this is going to be natural log of k over natural log of k plus 1. All that is then squared. All right. Do you agree that the left side is a little bit more than 1? You could imagine dividing the k up and you get 1 plus 1 over k, so it's like a skosh bigger than 1, but always bigger than 1, correct? Now let's think about the right-hand side. So if we think about the right-hand side, natural log of k divided by natural log of k plus 1. Isn't natural log of k plus 1 bigger than natural log of k? Right? Natural log is an increasing function, so if you go a little bit further out, natural log of k plus 1 is a little bit more than natural log of k. So doesn't that mean that what's in here is less than 1? Everyone agree? Less than 1? Because natural log of k plus 1 is bigger than natural log of k. So natural log of k plus 1, you're a little further out than natural log of k, so it's a little bigger. So that means that's a proper fraction, right? That denominator is bigger than the numerator. So this part in here is less than 1. Agree? And if you take a number less than 1 and you square it, it's going to get smaller. It's going to approach 0 if you keep doing it. Yep. So this side over here is greater than 1. This side over here is less than 1. So is that inequality true or false? Inequality is then true, right? If the left-hand side is always bigger than 1 and the right-hand side is always less than 1, then the inequality is true. So this is true, which tells us that we have convergence. So if that is true, and the limit of a sub k is 0, then we're done. That shows that we have convergence. So that's all it takes for an alternating series. Limit of a sub k is 0, and the terms are decreasing. Yeah, let's do one more here, and we'll be done. Then we can go hunt for food. We can go forage or whatever you do these days for food. Go dumpster diving, like my son does all the time. Like, really? You're going dumpster diving for food? I'm a college student, man. It's fun. Okay. So let's take a look at this one. The first step is the limit of a sub k. Bless you. And so a sub k, for the millionth time, does not include the switch. And what is that limit? K to the k in the bottom, that's the power tower.
Infinity.
That's going to be,
No, 0, 0.
they both go to infinity. The denominator is the power tower, which is the ultimate in terms of speed. So this is going to be 0 by growth rates. We can't do any more math than that right now on these. So then the question is, can we show that the terms are decreasing? So we want to show that a sub k plus 1 is smaller. So we have k factorial over k to the k. And then on this side, we have k plus 1 factorial over k plus 1 to the k plus 1. Got that. This will be simpler than it looks. Let's go ahead and do the thing that we did on the last one. Let's put all the factorials on one side, and let's put all the non-factorials on the other. So I'm going to rewrite this as k factorial divided by, I think you're comfortable writing that this way now, I think. And then over here, we're going to put the k to the k on top. Down here, we're going to write this as k plus 1 times k plus 1 to the k. Everyone okay with this factorial thing here? That and that are equal? And pull one off. So on the left side,
Sorry, what did you do?
okay. We won't finish this one. So k plus 1 factorial. Remember that factorial is repeated multiplication by subtraction by 1. So
the
this,
tail is the same with the k excited when the k was hit.
so it's going to be that. Like for example, if you have 5 factorial, you could write this as 5 times 4 factorial. Or you could write it as 5 times 4 times 3 factorial. All right, so it's that idea. We'll finish it up on next year. We'll finish it up on Tuesday. All right, well, have a good weekend. Do a lot of math. Do a lot of math.
So
Infinite series are a heavy lift.
what does it mean for the remainder in LCS? Does that mean?
So the remainder could be positive or negative.
Yeah.
So it kind of depends. Exactly. So if you look at the,
I've had math,
if you look at the next slide.
Oh.
9 straight semesters now.
Good question. Great question. So if your S sub n is above the convergence value, then your remainder is positive. But if your S sub n is below the convergence value, then your remainder is negative. Yeah. Great question. Very apropos.
Interesting.
Just way too much.
Yeah. Yeah.
I got that far. I don't know if I can prove it.
Mm-hmm.
I'll sit on it for a month or two.
Sit on it for a month or two.
And then come
You're
back
like a
and
hen.
smoothly over, sorry.
Oh, yeah. I'll go prove something else and come back.
Are we done? Are we done? Is it the 95 club?
Yeah.
Well, no, like in a specific semester.
But
I
that's
think it was
Monday,
like
so
my
it's
first semester of 8th grade.
Scary.
So we have